So here is our problem 2 now. Now, it's a very comprehensive problem. Problem number 2, if you look at the statement, it says analyze the given beam using stiffness method. F support A rotates by 0.002 radians clockwise. Support B settles down by 0.75 inch and support C settles down by 0.5 inch. Rotations and settlements are involved, so we will be writing the actual numbers now. So E is given 30,000 KSI, means it's a steel beam, and I is equal to 800 inches to the power 4. EI value, what will be the unit of this EI value now? E is kip per square inch and I is inch to the power 4. So 2 inches square will cancel with this 1 inches square. One is in the denominator, other is in the numerator. And we will be left with inches square. So kip inches square, but we will be using the kip and feet unit. So let's convert that into feet unit. So 300, this 30,000 multiplied by 800 divided by 12 to the power square, conversion from inches to the feet units now. So 30,000 multiplied by 800 divided by 144. So 156 is 0.6 kip feet square. This will be the EI, and wherever we have EI value now, we will be using this number now. Now description of the beam now. At A we have a fixed support, B we have roller support, at C we have roller support, and then we have overhang portion also 6 feet. Overhang span is 6 feet. So this free joint is joint D now. If we look at the total indeterminacy of this problem now, so at B we have 2 degrees of freedom, at C we have 2 degrees of freedom, and then at this D free end we have 3 degrees of freedom now. So it is becoming a 7 degrees indeterminate problem now. 7 degrees with the hand calculations, it may take maybe 3-4 hours to solve this problem. So now we need to act now smartly. And let's see if we can now, A information is again not given. So what we will do, we will ignore the axial effects now. Axial effects means 3 members we need to take out now. So 3 members if we take out, still it will become 4 degrees indeterminate problem. Now let's now do more, act more smartly. How can we do it? This overhang portion, very easily you can find out its member and actions and all these things. How? If we want to put its equivalent effect on joint C, so what can we do? We can find out its vertical reaction, we can put it here. And we can find its moment also, equivalent moment we can put at this location. Now we will discuss this, how to now reduce further. So if we can take away now this portion and put its equivalent effects here at joint C, we can reduce this to 2 degrees indeterminate problem, because then we don't need to find out the vertical, this translation here and the rotation here, because already we will take its effect at joint C now. So that way it will become 2 degrees indeterminate problem, which will be the rotation at B and rotation at C now, the way we did in problem 1, and then we can follow the same steps now. So how to involve the overhang portion, this is one now, the purpose of solving this problem. And then how to involve the rotations and the settlements. Now in sketch, if you see diagrammatically, the rotation 0.002 radius in clockwise direction is given at A. Settlement in the downward direction at B 0.75 inches given, and settlement at C 0.5 inch it is given now. Kinematic indeterminacy, we will solve this by 2 degrees. From 7 we reduced to 4 degrees, and from 4 then we took out this overhang portion. We included its effect. How it will be included we'll discuss in the following slide. So we reduced the problem to 2 degrees in determinate problem. Very conveniently now you can solve it manually. So here kinematic indeterminacy is 2. So 2 redundant giant displacements should be chosen, and we are ignoring the axial effects here. So quickly now you draw this sketch, and I'll be running you through these now various steps now. Now, remember here we have 4 kinds of loadings now. One is the directly applied loadings, which is 30 kip in the center, not in the center. If you look at this location 30 kip, now it is even off center. It is 10 feet from support A, while it is 15 feet from support B. Then we have UDL, B, C, and D span. So this is the direct loading now we have applied. Then we have the indirect loading. One is this rotation at A, settlement at B, and settlement at C. So now remember, while we are generating the ADL matrix, we will be now taking the effect of all these 4 kind loadings. One is because of the direct loading, which is 30 kip and 2 kip per foot, and the other one is the settlements. Now 3 kinds of, now these preconditions are involved, so we will be taking the effect of those one also. So once we find out the member indexes because of all these 4 loading conditions, we will be adding them up, and the resultant will become your ADL matrix. So with this now we move to the next slide now. Here now you see I was saying that we will be taking the effect of this overhang portion. So how much is the moment coming here? It will be 2 times 6. This will become your equivalent pointed load, and it's now centroid from this support is this L divided by 2 which will become 6 divided by 2. So this is simply WL squared divided by 2 now. So 2 times 6 squared divided by 2, we get this 36. And this 36, it is counterclockwise on the right hand side. So its effect at C will come in the clockwise direction. So clockwise. Now if it is corresponding to this D2 now, which is our unknown giant displacement, so this means our AD2 will become plus 36 now. So its effect is taken now into the calculations, and now we can ignore. And similarly, you can take its vertical also, which will be 2 times 6, and it will be acting in the downward direction. So its vertical effect is also taken. So when we draw the shear force and bending moment diagram, we can take this one also. Now you see here, this is your standard now 2 degrees indeterminate problem. Rotation at B, which is D1 in the clockwise direction, we designate this as unknown. And then at C, which is D2 in the clockwise direction, this is our unknown giant displacement. So rotation at B and C, they are taken as redundant giant displacements, D1, D2 unknowns. And AD1 now corresponding to D1, we don't have any externally applied action now, so that is equal to 0. At C now we have a clockwise moment, which is 36 kip feet, so we include that as 36 kip feet. So step number 1, we have designated our D's, and we have now created this AD matrix 0 and 36. Next now we go and generate the ADL matrix. So this is now your basic kinematic determinant structure. At B now you can see we have a fixed support, and at C also we have a fixed support. Now here now to create the ADL matrix, as I said, 4 kind of loadings are involved. So first we deal with the due to direct loading, which we will call ADL prime. Because of the rotation at A, we will call it ADL double prime. Because of the settlement at B, we will include that effect as ADL triple prime and then tetra prime for the settlement at C. So first now you see this is the basic kinematic determinant structure now. And you see the loads also 30 kip and 2 kip per foot. You can see here. The overhand portion already we included that in the AD matrix, so don't worry about that anymore now. Now, how this now let's verify this one. So PAB square divided by L square. This is off center, that is why A is 10 feet and B is 15 feet. So take out your calculators and now start now following me in these calculations. 30 times A is 10 times B square will become 15 square. So divided by multiplied by 15 square and divided by L square. L is 10 plus 15, 25. So 25 square. So this is becoming 10. This is maybe I made some mistake. Divided by L square, PAB square divided by 8L square. It should be, I think, 8L square divided. No. Let's now verify this. PA, it was actually PL divided by 8. So, can you go back to the equations now, CR? I need your help here. So 30. Sure. Yeah, so can you go through the calculations? What number we have? 30 multiplied by 10 multiplied by 15 square divided by. We need to verify this value now.
सर 30 multiplied by 15 square multiplied by 10 divided by 25 square करने से हमारे पास 108 आता है.
कितना आ रहा है?
108.
No, so that is not okay. Then we have 168.4. So it is divided by maybe the original equation was. Let's verify this now. So we were having actually PL divided by 8, correct? Now,
yes,
how with PL by 8, it was the original one, means it was P times L by 2 and L by 2 multiplied by L by 2 square. Why I am putting L? Because L by 2 was A and B was also L by 2, correct? And divided by now L square. So if we put L square, so how much we get from this value now? We get PL cube in the numerator divided by 8, the 4 times 2. So divided by 8 and divided by L square. So this is how we were getting PL square divided by, it was PL divided by 8 now. We got the same value. Now, if we use this one now, so B is 30 and A is 10. And then we have 15 square and divided by this L square. So L square is becoming 25 square. So 30 times 10 times 15 square divided by 25 square. This is becoming 108 and we have 164 points. So this is not correct. Let's confirm now the right hand side. So the right hand side will become equal to PBA square. So 30 times 15 times 10 square divided by 25 square. So 72. So it means the one
yes,
we are
yes,
showing. Yeah, yes, yes. So it means this is wrong. Then we need to make a correction here. This should be 108. 108 kp. And these reactions now, how to find these reactions? You will have to take into account the balanced moment also. Look, how we are going to find this quickly. It will be, let's say I'm finding out, verifying this 19.44. Right, so 19.44, from where it is coming? It is coming, I am taking moment about this point is equal to 0. Summation of MB is equal to 0. So what do we have? We have 30 times 15. 30 times 15 divided by 25. So if the unbalanced moment was not there, and if only 30 was there, and if it was simply supported, so 18 kip was coming to the left support now, and 12 kip was going to the right. But now the unbalanced moment we need to now balance. So how we are going to balance? If you see here, 108, it is more than 30. So we need to balance this clockwise, counterclockwise with the clockwise couple now. So whatever reaction now coming here, it will be looking upward. Now it will be upward directed. So it will be equal to plus now. Upward means it will be adding with this 18 we already found. So it will become 108 minus 72 and divided by its moment arm, which is equal to 25. So divided by 25. Divided by 25, it is coming 21. Is it correct?
Yes, सही आ रहा है सर इस तरह.
ना कितना आ रहा है? 19.44 आ रहा है.
Yes sir, 18 वो पहले आ रहा था, 1.44 बाद में इसको कैलकुलेट करने से आता है. तो
अच्छा ठीक है. अच्छा मैंने वो 21 की बजाय what I did, I divided by 8, so it's a mistake actually. It should be so this 19.44 is correct.
Yes sir, it's correct.
18 आ रहा था ना, and then we have plus. Now the difference of this 108 minus 72 and this divided by 25. 19.44. So it means the previous value written here, it was wrong. Correct? Maybe what we do in making these slides, we copy from the previous one. So the number is also coming, and then we forget to change the number. So that was the situation actually. But now if you see this AB span, it is perfectly in equilibrium in all the member actions we found. Coming to the right one now, WL square divided by 12 now, that is the equation for the UDL. So let's verify this. 2 times L square means 25 square and divided by 12. So you see 104.17 and 104.17. We don't have any unbalanced moment. 104 is balancing the 104. So half of this load will come to the left support, half to the right support. So WL divided by 2. So 25 kip and 25 kip. And from here now we are going to generate our ADL prime now. ADL 1 prime will do what? Corresponding to D1, which is plus 72 minus 104.17. So this is minus 32.17 is coming. And then corresponding to D2, we have this ADL 2 prime, so 104.17. So this is 104.17. Are you with me? CR?
Yes sir.
Okay, so with this now ADL 1 prime matrix is generated. And remember again, your AML values will be coming from this one. AML and ADL values are coming from this diagram. Next now, we need to take the actual rotation which was at support A now. And it is provided to which one? To the basic determinant structure now. So this is also a kind of loading now, which is the indirect loading. So here clearly, if you see step number 2, part 2 is due to indirect loading, which is 0.002 radian clockwise rotation at A. And the values we will be getting will be ADL double prime. Now, when rotation is given, so at this end, in the same direction moment will be generated. That will be 4EI theta divided by L now. So we can verify this value now. So 4 times EI already we calculated in kip feet unit, which was 1 and 566.67. Now, rotation, we have theta value, so 0.002 we put and divided by this L, which is 25, which is equal to 53.33. So here you get 53.33. At the far end in the same direction by the same magnitude, so 26 point, this is rotation, so half, and in the same direction it will go to the far end. So if we divide this by 2, so we get 26.67. Now the balancing now couple, how we find out the unbalanced now couple, we add them up, 53.33, and this is plus 26.67 and divided by the moment arm, which is 25, so 25 square, so divided by 25 again, so it is coming, I have something wrong with the calculations, 53.33 plus 26.67 and divided, okay, this is equal to, and then this whole divided by this 25 square. So this is coming 3.4. This will become, this will become 6 EI. So 6 EI already we have these numbers. So 53.33 and we have 26.67 and this divided by 3.2. Okay. So unbalanced moment divided by the moment arm, so divided by L, 25 only, which is coming 3.2. Now what we are doing here, you don't need to go against 6 EI theta divided by L square, because this will become a lot of calculation. So what we do, we add this unbalanced moment algebraically, 53.33 plus 26.66 and divided by the moment arm, which is 25. This way we get this balancing couple, which is 3.2 and 3.2. Now, right hand side, we don't have any activity, so all the member inductions will be 0 there. Now, corresponding to D1, what we have now, we have 26.67 clockwise. So this is how ADL1 double prime 26.66, and then corresponding to D2, we have 0. So ADL2 double prime is equal to 0. So we took the effect of this 0.002 radians clockwise rotation. Now let's include the settlement at B now. So what will happen now, we will clamp this A joint, clamp C joint, and that settlement, how will it will be provided here? We will provide a roller guide here, the guided roller, and we will slide it in the downward direction. So what will happen now? You see here, it is coming down. These are fixed, doing nothing here, and this is now that settlement now, which is 0.75 inch. We convert this into 0.0625 feet now. The member end actions generated here, the corresponding member end actions, where it will give you the ADL triple prime values now. Let's verify this now. AB span we are taking. When this settlement is coming, so how much is going to be the moment generated, and how the moment, the direction, it will try to come back. So it means clockwise moment is generated. If you follow this cursor now, this end is trying to come back to its original position. This will give you the sense of this moment. And from where this 100 is coming, this will come from 6 EI was 156.67, and then this delta is 0.0625 feet, so 0.0625 and divided by L square, which is 25 square. I am running the numbers also. It is coming 100, and exactly 100 we are showing. Then to the far end, the same direction and same magnitude, so 100 we have here also. Now the balancing couple, now we need to find out. So 100 plus 100, 200 is the unbalanced moment. We need to balance it by the couple, so divided by the moment arm, which is 25. So 200 divided by 25, 8 kip, it is now the clockwise couple now. So we found all the member inductions for member AB. BC now we take, again, to fix its direction, this displaced location, it will try to come back to its position. So it means clockwise movement is going to bring it back now. So this is the direction now. Span is the same, EI is the same. So 6 EI delta divided by L square again. So 100 in clockwise at the far end and also 100 in the clockwise, and this is the balancing couple. Now ADL1 triple prime will become 8 corresponding to D1 now. So 100 minus 100 is 0. So 0 we are putting here corresponding to D2. Clockwise means positive and magnitude is 100. So 100 we are putting here. So ADL triple prime is completed. Now we are left at the settlement at C support now. So A and B we keep fixed and we slide down this C support by 0.5 inch now as given now. So here you can see and how will be the configuration. So this is here the roller guide is actually applied and it is coming in the downward direction. Moments now, member and actions we are producing, and this will give you triple prime now, ADL tetra prime now values. So this will try to come back now. So means counterclockwise movement will be generated. Far and also clockwise by the same magnitude, and this is the balancing couple. Now again you can see 6 EI delta C divided by L square, so 66.67 is coming. Delta is 0.014 now feet here. Far end it is the same, and this is the balancing couple. So ADL1 tetra prime will become corresponding to this D1 now, which is minus 66.67, and value is recorded here. Corresponding to D2, we have this minus 66.67. So again, minus 66.67 is recorded here. We don't have any contribution from the BA support in case of the ADL1 tetra prime. So again, correspondingly now, we need to now add all these 4 numbers now to get the cumulative ADL now. So ADL1 now, ADL1 prime, double prime, triple prime, tetra prime. Correspondingly, we add those values. So minus 72.17, this is becoming your resultant ADL1 matrix. And similarly, ADL2, we add them the corresponding values and we get 137.50. This way we complete our ADL matrix now. So with the ADL matrix now completed, what we do now, we go to the stiffness. It's a routine. Quickly I'll be running over it. This is now first step of this. First now, what we do now, we give a unit rotation at D1. So D1 is equal to 1 and D2 is equal to 0. We are keeping. Here you see now this statement here applied to the sketch. Now let's verify this value now for the AB span. So this will become 4. EI was 156.67 and divided by L, which is 25. So 246. So 246.67 here. Far end divided by 2 in the same clockwise direction divided by 2, and then the balancing couple now. So if I quickly you can do such kind of numbers. I multiply this by 1.5 and divided by the span 25. This way we are going to find out this quickly. So simple mathematical operations. How would you find out these member and actions now? Similarly, for the right hand side, we do the same thing and we find out all these member and actions now. S11 will be corresponding to this one location now, and it will be the algebraic sum of these moments generated. Why we are taking moments? Because these are corresponding to the unknown giant displacement, which is rotation now. So plus 246.67, and here again 26. This is whatever number is. So 246.67. We add them up and we get S11 is equal to 43.33. Similarly, at location 2, which is at 2 due to 1, which will become S21, it is this plus 143.33. So the first column of the stiffness matrix is generated. And remember, this is the diagram which will be giving you the values of AMD matrix also. Right? Accordingly, you will be taking your values from here. Now, second column. So second column, what we do, D1 we keep fixed now 0, and D2 we apply a unit clockwise rotation now. So unit clockwise, and this is the deflected shape now, how it is going to be. Tangent here, it will be again clockwise. Again 4 EI theta divided by L, 2 EI theta divided by L, 6 EI theta divided by L square. Now S1 due to 2 now will become 1, 4, 3. So here we write it. And S22 will become equal to this number which is written here. So this is 6, 7. So this should be also 6, 7. It's not 6, 2, it is 6, 7. So here now, this we see here now, this stiffness matrix we have created. Now, and remember, AMD second column will be also generated from this diagram. So next now we go and we solve this equilibrium equation, step number 4. We have all these numbers now. ERI value is already embedded in these numbers now. So we just simply take the inverse of this, multiply with the difference of this matrix. Already we found ADL, and you see here it is coming with the algebraic sign now. Whatever it was, and it was minus and this was plus. And finally we find D1 and D2 now. One is 0.0026 and D2 is coming 0.0051 now. After this, the step number 5, which is the member end actions. Let's we identify these member end actions now. AM1, 2, 3, and AM4, and here moment, and this moment now. So let's now go and find out this one. So AML will be corresponding to this one now. So AML1 is how much? It is corresponding, and it is coming 24.24. Now you make a note of this one. AML1 is equal to 24.24. I didn't see this solid number in the previous slides, but from where it is coming, so let's verify this one value. Rest you can verify that. AML1 I will be verifying. Remember, AML will be coming from the diagrams from where we created our ADL matrix. So let's go there now, and 4 now things were contributing there. One was the direct loading, rotation at A, then settlement at B, and settlement at C now. So let's take those effects and verify this 24.24. So let's go there now, and here now, this is now the diagram. This is now, so from direct loading, which is ADL prime, here is coming 19.44. So make a note now, this is 19.44, one contribution, so 19.44 I'm writing on my calculator. Then due to this rotation, due to this one now, we have ADL1 double prime, so we have here minus 3.2 now. So minus 3.2 I put. Then from this settlement at B, we have effect of plus 8. So plus 8 I'm putting. And then settlement at C, we have 0 now from here, vertical reaction 8. So plus 0. So if you add them up, exactly 24.24 we are having. So for the rest of the location, you complete the ADL matrix by this AML matrix here in this case by the same procedure. So you can go corresponding values you can pick from all those four sketches, and this way you can complete this one. Now to complete the AMD matrix, where is it now? This is corresponding to first element of the AMD. First column we will be generating from here. Which one is this sketch now from where we applied a unit rotation corresponding to D1 now. And already we generated first column of the stiffness matrix from this one. This is the same one. You don't need to redraw this again. Just go to that sketch and grab your values. So AMD11 you see here. What is the reference for these one? Now again the AM values we selected. So AMD1 will become minus 1600 now. AMD21 will become plus 1600. This is minus 1600, and here this is plus 1600. AMD51 will become plus 1, this 4 3s, and AMD61 will become plus, and this AMD7 also plus. You should be matching its actual direction with the assumed direction, this one. And this is our positive reference, and here also you can see. So this will give you the first column of the AMD matrix. The second column is going to where we apply the rotation corresponding to D2, and we completed the second column of the stiffness matrix. Now these are those values now. So AMD12 now is 0, AMD22 is again 0, AMD32 is minus 1600, and this is plus 1600. Similarly, AMD51 is 0, 62 is 0, and 72 this one, and this, and now you see all these minus 1600 plus 16 minus, as I said, and this is 0 0 minus. So AMD matrix is complete. Rest we need to put this now in this equation, and the matrix algebra already we have the rotations now. We just completed AMD, AML already we have. So find out the product of this, sum it up with this AML matrix, and get the values of AML. And then after this AM, we put them on the sketch. It's a routine now, this one. And after this, what we do, we draw the bending moment and shear force diagrams. So draw shear force and bending moment diagram, you should be able to do. Let's verify quickly. 25 plus 6 is coming how much? So 25, 31 is coming. 31 times 2. So because of UDL, we have a downward force of 62 kips, and plus 31, we have 30 kip we have down. So 92 kip I'm looking at. So 92 kip should be upward also. So we have 20.03 plus 9.93 plus 26.32 plus 23.68. So this is coming less, and what is the reason? It is upward and downward should be equal. Did we do some mistake now? Yeah, okay, I got the point now. So the point is plus 6 times 2 also we need to include. Yeah. So actually this effect is not included here. I said that finally we need to include it as effect. So this is actually shear to the left of this 23.68. It is shear to the left of this C support, and shear to the right of this support will be 6 times this 2, which is 12 now. So we need to show that one also, which is the shear to the right, this one. So that 6, if it is included, then we have 91.96, which is approximately equal to 92. So you need to show that one also. And after that, you will have to try the shear force and bending moment diagram. So with this, we are done now with the this one. If I go here, so I need to slide this. This one I need to slide this to the left, and this number is again we need to move this. So, but anyways, but here now we need to show another arrow, and with that we need to show this 6 times 12, which is 12 kip in the upward direction. Now we go to the next problem now, and one student was asking me if rotation and let's say settlement both are involved, so how we are going to handle that situation. So he should be looking very seriously at this problem now. Here what we have A, B fixed ended beam, but in the now at 10 feet from this support A, we have internal hinge now. So the problem is analyze the given beam using the stiffness method now. So as the internal hinge is not in the middle, it means this θ1 rotation at A, it will be different from the rotation at B now. How? Very simple geometrical problem. This θ1 will be equal to tangent inverse of delta divided by this 10 feet. But this θ2, which is rotation at B, it will be equal to this delta divided by 20 feet now, which is means this θb will be half of this θ1 now. At the bottom, if you come here now, this θ1 will be equal to this rotation now, if you are following my this cursor, and θ2 will be equal to this rotation now. Means at this hinge, we will be having two independent rotations now, θ1 and θ2, and those are becoming our unknowns now. So two displacements now are 2 degrees of freedoms because of this θ1 and θ2. And one is the vertical settlement now. So this vertical now deflection, that will become our 3rd degree of freedom. Now horizontal effects we are ignoring. Otherwise, if horizontal also if you include, then it is becoming 4 degrees indeterminate problem. But in this case, it is 3 degrees indeterminate problem, θ1, θ2, and this delta. How to handle now this problem in this stiffness method? Cases solved. Okay. So first, let's identify these θ1, θ2, and this delta. Now I don't want to put these theta's and deltas. I would straight away I want to go by the these notations now. So you draw this sketch quickly now. Show the internal hinge fixed ends now, and throughout it is loaded with 1.5 kick per foot now. It's a very interesting problem, and we will solve this quickly now. It is a 3 degrees indeterminate problem. These 3 degrees I'll be showing you in next slide now. Okay, let's move to the next slide now. So here rotation now, θ1 we are showing by D1 clockwise direction. θ2 we are showing by D2 clockwise direction, and the delta we are showing by D3, it is in the downward direction. These are our reference now positive directions and our reference unknown joint displacements also. So 3 degrees indeterminate problem, D1, D2, and D3 now. If now, let me ask you this now, if this internal hinge was at 15 feet now, which is the center of this span, in that case, D1 will become equal to D2. So we take this one independent. So this is becoming 2 degrees indeterminate problem. If you solve this by 3 degrees, okay, well and good, but at the end, you will know that D1 was equal to D2. So just by observation, you can do that by solving a 2 degrees indeterminate problem. So D1, D2, D3, we declare them as now unknowns. Corresponding to those now, let's see now, corresponding to D1, do we have any externally applied moment? No. So it is 0. Corresponding to D2, do we have any externally applied moment now? No. So AD2 is equal to 0. D3 now, corresponding to this, do we have any externally applied now action, now force now? No, again, so this is equal to AD3 is equal to 0. Let's, a load of 5 kip was applied downward at this internal hinge now, which was corresponding to D3, and it was in the same direction downward, so then we include that 5. So यहाँ पे आप 5 include करेंगे. If we don't have, so we put this. So our ADL matrix is generated now. From the basic principle now, what we do now, we generate now the this is now your basic determinant. What we are doing at the hinge location, we are just putting that fixed support now. So this is your basic kinematic determinant structure, or this restraint structure. Now what we do now, at this fixed ended beam, we find out all the member end actions now. 10 feet, you see here the hinge location at this. Why? Because the corresponding actions we will be looking for now. So WL square divided by 12, we are getting all these member end actions by using that simple relation. Now, corresponding to D1 now, if you see this 12.5 cap, it is in the same direction. So 12.5 now, this is becoming our ADL1 now. Corresponding to D2, we have this minus 50 now, which was rotation to the right of this hinge now. So minus 50 is the corresponding, but it is in the opposite direction. So we take minus 50. Corresponding to D3, which was the settlement at this location. So we have this 7.5 and 15 reaction board are in the upward direction. Our settlement, where D3 was in the downward direction, means these actions are in the opposite direction. So we have minus 7.5 and minus 15, which is minus 22.5. So we complete this minus 22.5 now. Remember, your ADL matrix is coming from here, and your AML matrix again will be coming from this sketch now. Now, generation of the stiffness matrix now. So how we generate it, turn by turn, we will be giving a unit displacement now. Corresponding now, we are coming how to give corresponding to D1 now. So you see here, the left side, we are releasing, we are providing a hinge support here. Rest, all the locations are fixed now. E1 at the hinge now, the right side of this is fixed now. That 4EI divided by L, 4EI theta. So 4 divided by L is how much? 10. 4 divided by 10, this is how we get this action produced here, 0.4 EI. At the far end, it will be half of this, so 0.2. And this is 6 EI delta, 6 EI theta divided by L square. So these are this is the couple now, which are the vertical reactions at A and at the hinge now. At the right hand side, we don't have any activity, and it is not going to let the moment transfer here because it's a fixed support here. So all the member end actions for this right portion are 0. Coming to pick the values of stiffness coefficient matrix. Now remember, the first column of this stiffness matrix will be generated from here, as well as the AMD first column is going to be generated from here. Now corresponding to D1, we have this 0.4 EI. So this will become your S11. S at 1 due to 1 now. So 0.4 EI, and here you see the value. 2,1, which is the action here now, which is 0. So S2 due to 1 is equal to 0. So we have written this value equal to 0. S31, which will be in the direction of D3 now, which was downwards, but we have here what? Upwards. So minus is coming here, and its magnitude is 0.06 EI plus 0 from the right portion now. So minus 0.06 EI we have included. That easily you can create the first column. Second, now corresponding to D2. Now here all this what we are doing is written. D1 is equal to 1 we are applying, and D2 we are keeping equal to 0, and D3 also we are keeping equal to 0. Second, now corresponding to now D2 we are applying a unit now. Here you see theta is equal to 1 we are applying, and the left hand side rotation we are keeping 0, means it is fixed now. So this will become 4 EI divided by L. L is 20 now instead of 10. So 4 divided by 20 is 0.2 EI. Far end is half of this, and this is the balancing couple now. This will generate the second column of the stiffness matrix, which will be S at 1 due to 2, at 2 due to 2, and 3 due to 2 now. S11, we don't see any moment now here in this pen corresponding to D1, so it means it is 0, which is written here. And it must be matching the S21, which we found in the previous slide. S22 is now this value, which is 0.2 EI. Since is clockwise matching the D2, so 0.2 EI. And then S32 is now the summation of the algebraic sum of these vertical reactions corresponding to D3 now. So we have plus Y plus because it is the same downward direction as that of D3 now. So 0.015 from the right portion, and from the left portion we have 0 now. So S32 is coming 0.015 EI. And remember, third column of the second column of the AMD matrix will also be completed from this sketch. Next, now the settlement is now involved. So rotation already you knew from up till now discussion, but now when the settlement is involved, how to include that one. So now that specific student now who was asking, so now how we are including that one, he should be very careful now and should pay attention. Now, how we apply the unit settlement? Now we apply a roller guide. The other locations we keep fixed, and because of this roller guide, we slide this position in the direction of D3 now by a unit displacement. Now 1 is provided here, so this is the new location, and this is now the distorted now shape of the modified shape because of this settlement of this sketch. Now original is this top one straight line, but it is coming to this one now. Left portion, if we select now, it will try to come back to its position now. So this is how this counterclockwise direction we have found. It will be 6 EI delta divided by L square. So L square is 10 square means 0.06, this member and moment. Far end the same direction, same magnitude, and this is the balancing couple. Similarly, for the right portion, again it will try to come back. So when it can try, when the moment applied is in the clockwise direction. Far end moment, and this is now the balancing couple now. How we pick now the values of this third column stiffness coefficient matrix, S13, S23, and S33. S13, it is corresponding to 1 now, which was D1. So it is minus 0.06 EI. Why? Because it is counterclockwise. Our assumed D1 direction was clockwise. So here we record it. S23, it is clockwise 0.015, so 0.015, and S33, it will be the summation of this one, and it is in the D3 direction, so both are positive. So 0.012 plus 0.0015 EI, which we sum up when we add them up, so it is coming 0.0135 EI. S33 is generated, and third column of the AMD matrix is also generated from this sketch now. And here you see what we are doing now. D3 we are providing equal to 1, which is here, and D1 and D2 we are putting equal to 0. So here you see the roller guide. It is not now allowing any rotation. It is only allowing this sliding in the vertical direction. With this now, this you see here now in a very nice form at the bottom in the center of this screen now. Here you see the S matrix generated now. EI is obviously there, so you outside the bracket now you can take out this EI count. After this now AD matrix is generated, ADL is generated, stiffness matrix is generated. So now we are in a position to move to step number 4 now. We use this equilibrium equation and we find out D1, D2, and D3. So this is D1, D2, D3. I don't need to explain now this matrix, simple matrix algebra now. Here you see here it was with I, but when we take inverse, so it is becoming 1 over EI now, and this is the D1 over EI values now. With this now, we can move now to step number 5. We are finding out these member indexes we are selecting. Vertical reaction at A is AM1, vertical reaction at B now AM2, moment at AM3. Now hinges, what far I'm finding out AM4 and AM5. Now already it's an internal hinge and these should be equal to 0. If not 0, something is wrong with the calculations. But let's verify this 0. So that's why I'm using this. AM6 is the moment. So AM1 and AM2. So now it's easy now how we pick these values. You see, these are now AML1 corresponding. Again, reference is now the one we selected for the AM. Now that is our reference now. So we go to the, from where we generated our ADL matrix, we are completing our AML matrix from the same one now. AML1 will become your 7.5, so we recorded 7.5. AML2 corresponding to this is this 15 value, so we write this 15. AML3 corresponding value is now it's in opposite direction, so minus 12.5 now, so minus 12.5. AML4, it's in the same direction, so plus 12.5. AML5 is this one, it is in the opposite, so minus 50. And AML6, it is 50, so 50. AMD matrix now let's generate, and as I said, it will be from where we generated the first column of the stiffness coefficient matrix, and this is that one where we give a unit rotation corresponding to the D1. This was that one. So now AMD11 will become your minus 0.06 EI. AMD21, which is at B now, it is 0 now, and similarly you can pick these other values also referring to this one. Now, a second column of the AMD matrix where we apply a unit rotation corresponding to D2 now, and the corresponding values you will be taking now from here. Make sure that you get the appropriate sign also. And then third column will be generated where we give a unit translation corresponding to D3. Now, already you have these values. So from here now, from here, if you remember, the third column of the stiffness matrix was generated. So now third column of the AMD matrix we are generating from here. So this will become your AMD13, and this will become your AMD32. And this way now we complete, this is now your completed AMD matrix now. Rest is the simple now mathematical operation. Find out the product of this, add this with this one, and you find out all the member indexes. And you see here AM4 and AM5, how they are becoming equal to 0 and 0. This is, you see the reaction on. So AM3 now, we assume this in the clockwise direction, but it is coming in counterclockwise, so we put this in the counterclockwise direction. All these member indexes corresponding, you can see AM1, 24.38, AM2, it is 20.60, AM3, 4, 5, and this is 6 one now. And after this, what we do, we draw the shear force and bending. Here again in the bending moment at the edge, you can see it is coming 0 now. So this is the complete shear force and bending moment diagram. And after this, we have these assignments. So if you have any question about the assignments, you can ask from the CR now. And these are the references. Now you can turn on your mics now. You will be running to the next class also, but I'm here now to answer your questions. Now, especially that student who asked me if rotation and settlement is also, deflection is also involved at a giant, how we deal with it. So I hope this problem number 3 covered that situation. Okay.
Yes, sir. Clear.
Clear?
Yes, sir.
Rest of the students, CR Mr. Sijad is saying it is clear, but what about the other students now? Okay, if I'm not getting any now question, I assume that you go within this week now. Following week, we are not going to have any class, right? As now you got the exam schedule also. So the week of 22nd June, it will be your exams now. So these 3 problems, you go 3-4 times each problem now, and you ask yourself the questions that from where these numbers, if they are clear, it's fine. If they are not clear, you go the second time, third time, fourth time. If you cannot solve them, then next lecture maybe not becoming the next lecture, you can ask me questions now. Remember, now we have modeled these problems now for the stiffness method. The same mold we will be using for the rigid joint frames, and we will be using this for the trusses also. So our part of the remaining 3-4 lectures, again we will spend by using the same now 5 steps. Exactly the same steps we will be following. So make sure that you properly go, and remember, your examination will be within now the topics whatever we covered till today. Means the stiffness, the beam solution by the stiffness method will be also included. You got the derivations, you got the comparison, you got the now the definition of the various terms, and then the method of using of these methods, and what is kinematic indeterminacy, how we find it, the statical indeterminacy, internal, external. You should be clear. It's a lot of work, so you need to work very properly and make sure that you clear yourself about the midterm examination from the department. Okay, so with this, if you don't have any question, I'll say good luck to you, and maybe we meet then after 2 weeks. Mr. Sajjad, CR, any question?
No, sir.
Okay, so then bye-bye from my side.
Thank you, sir.
Okay.